All right, we're going to be talking here about simple harmonic motion. Now, simple harmonic motion is a couple examples in real life, or if you have like something on a spring that's like bobbing up and down on the spring, and it keeps going to the same height and down to the same low point and just back and forth between those two. That's what we call simple harmonic motion. Or if you have a pendulum that's swinging back and forth, like if you have an old-timey clock that has a pendulum that swings, that pendulum, the rest position would be like straight up and down, and then the displacement of it is how far it swings beyond that rest position. That's another example of harmonic motion. Another one might be if you have like a buoy or something floating, tied down to the bottom of the ocean, and then you have the waves coming through, and as each wave goes through, the buoy bobs up and down with the waves. That's also simple harmonic motion, right? So harmonic motion is basically anytime you have something moving back and forth between the same two values, and it does it at a consistent rate, you've got simple harmonic motion, right? And since it's something moving back and forth, or like a wave going up and down, it can be modeled by trigonometric functions, by sine and cosine functions, because if you remember the graphs of sine and cosine, they're waves that always go up and down between the same values, right? So they're perfect for modeling things like simple harmonic motion. All right, so the formulas or the equations for simple harmonic motion. The displacement y of an object at time t. Right, so remember, displacement is, let's say it's a spring bobbing up and down. The rest position would be, that's your starting point, basically, or not your starting point, but the rest position would be like if it's just hanging there and it's not moving at all, wherever it hangs to, that's what we call the rest position. The displacement is like how far above and below that rest position does it go. Right, so y here represents that displacement above its rest position. Or if you're thinking about like the waves in the ocean, if it was just flat, calm ocean with no waves, that would be your rest position. And then your displacement would be like the height of each wave as it goes up and down. That gives you your displacement above just that middle level, right? So your displacement y of the object at time t, y is equal to a times sine of omega t, or y equals a times cosine of omega t. Right, now that symbol right there that looks a lot like the letter W, that's the Greek letter omega, which whatever mathematician decided to make this formula decided to use that letter omega. If you call it W, that's fine. It looks like a W, but technically it's the Greek letter omega. And really, you can put any letter in there. It doesn't really matter what letter you use to represent that value. All right, now, what these numbers here, the A and the omega, what they represent and what they do when we're dealing with simple harmonic motion relates directly back to the graphs of the sine and cosine functions. So if you haven't seen the videos I did about the graphs of the sine and cosine functions, the things we're going to talk about here are basically directly from what we talked about with the graphs of sine and cosine. Right? So the amplitude of my graph is going to be the absolute value of A, right? That number out in front of sine or cosine that's multiplying the function, that's the number that determines how high the wave goes, or how high the spring bounces up or down, or how far the pendulum swings to one side or the other from its rest position, right? So the amplitude is the maximum displacement from the rest position, right? And that maximum displacement is given by that number in front of either the sine or the cosine function, whichever one you're working with, right? The period is 2 pi divided by omega. Now, when I did the videos on the graphs of sine and cosine, the number we had multiplying the variable, we used a k instead of an omega. But the omega here represents the same thing as the k. If you watch those other videos I did, it's the same thing as that k that was there. Right? That k determines what the period is going to be. And what the period means is, when we have harmonic motion or when we have waves, they're periodic. They repeat the same behavior and over again, right? For something bouncing on a spring, it goes all the way down, it comes all the way back up, it goes back to where it started. And then it does the whole thing again. And then it does the whole thing again, right? That period is the time it takes to complete one cycle. So if it's starting from the middle position, all the way down, all the way up, back to the middle, however long it takes to do that, that's the period. And that period is given by 2 pi divided by omega, whatever number is there multiplying the t inside my sine or cosine functions. That's going to determine the period of my harmonic motion, right? And then here we have frequency. Frequency is not something we talked about when we talked about the graphs of sine and cosine, but it's basically just the reciprocal of the period, right? Period is 2 pi divided by omega. Frequency is omega divided by 2 pi, right? It's just flipping that fraction over. And what the frequency is the number of cycles per 1 unit of time. Right, so let's say I have a pendulum swinging back and forth, and let's say its period is try to put this in something that'll be easy. Let's say its period is 1/4 of a minute, right? So let's say it takes a quarter of a minute for it to swing all the way from one side all the way there and then all the way back, right? If the period is 1/4 of a minute, the frequency would be 4, because it does 4 of those in one single minute, right? So that's what we mean by number of cycles per unit of time. If one cycle takes 1/4 of a minute, you can do 4 cycles in one single minute, right? The unit of time is like your 1 minute there. And that's just an example I made up off the top of my head. But I'm going to do an example in a few minutes, or less than a few minutes, where we actually go through and find all these things for an actual real life example, right? But the frequency and the period are just reciprocals of each other, right? How long it takes to complete one cycle is your period. How many cycles you can do in 1 minute or 1 second or 1 hour or whatever your unit of time is, that's your frequency, right? And then the amplitude, again, that number in front of the sine or cosine, that's your displacement. Whatever your rest value is, how high above and below that do you go, that's your amplitude, right? Which, when we're talking about the graphs of functions, it's like the vertical stretching of the graph, which gives you the height of those waves. All right, and then the only other thing here to talk about before we do the example, there's 2 different ones here, right? There's a sine function and a cosine function. So how do you know which one to use? Well, if you remember the graphs of the sine function and the cosine function, the sine function, at 0 starts at the origin, and then it goes like that, right? The cosine function at 0 starts at the maximum point, and then goes like that. Right, so which one of these we use when we're modeling harmonic motion depends on our starting point. If we're starting at the rest value, which would be like our 0 value, then we're going to use the sine function, because the sine function starts along that middle value, right? That rest value. Whereas if we're starting at the high up value or the high low value, that doesn't make any sense at all. The highest up value or on the lowest value, then we're going to use the cosine function, because the cosine function starts at that maximum value. It starts at like that highest amplitude, right? So if at time 0 we're at the highest amplitude, we use the cosine function. If at time 0 we're on that middle rest position, then we use the sine function, right? And that's why we have the 2. It all depends on where we start. All right, and we'll see that in some of the examples that we do working with harmonic motion. All right, I'm going to pause this here and erase all these definitions and stuff and put up the example that we'll work through to see how this stuff works. All right, the example I put up here, the displacement of a mass suspended by a spring is given by the equation y equals 10 times sine of 4 pi t, right? And where y is measured in inches and t is measured in seconds. All right, and we're asked to first find the amplitude, the period, and the frequency of this harmonic motion. All right, so we do have something in that harmonic motion form, right? Our a is the 10, the number multiplying the sine function, and our omega is that 4 pi, right? That's what's multiplying the t inside of the sine function. All right, so my amplitude is going to be the absolute value of 10, which equals 10. All right, whatever number is out front there, that's our amplitude. Now, if that's a negative number, we just take the absolute value and make it positive. Right, so that's going to tell us how high our graph goes. So it's going to go from 0 up to 10, and then also from 0 down to negative 10. And it's going to keep bouncing back and forth between positive 10 and negative 10. Right, that's what that amplitude is telling us about the graph of this function, and also about the behavior of this mass. Right, from wherever its rest position is, it's going to go down 10 inches, and then it's going to go back up 10 inches, and then bounce back up and down between, a positive 10 and a negative 10 inches. There's our amplitude. All right, the period. All right, period is equal to 2 pi over omega. And omega, remember, is that number that's multiplying the t inside the sine function, which the number multiplying the t is 4 pi. All right, so our period is 2 pi over 4 pi. All right, now, again, this goes back to, if you watch the videos that we did on the graphs of the sine and cosine functions, to find our period, it's always 2 pi divided by whatever number is multiplying the variable, right? Because the reason it's 2 pi divided by that is the general period of the sine and cosine functions is 2 pi. If I just graph y equals sine of x or y equals cosine of x, the period is 2 pi. That's how long it takes before the graph starts to repeat itself. So if I have a number multiplying the variable there, the t, that's going to affect the period, and it's 2 pi divided by whatever that number is. The normal period divided by that extra number that we threw in there. Now if I have 2 pi over 4 pi, well, the pi's there are going to cancel out, and 2 over 4 can be simplified into 1/2. All right, now, since we're doing a word problem here, I neglect to do this up above, but we really should put units on what we have. So my amplitude here is going to be 10 inches. Right, that's how far our weight is traveling above and below its rest position, 10 inches above, 10 inches below. Our period is going to be measured in the time, which is seconds. Right, so if we start from our rest position, our weight is going to go 10 inches down, 10 inches up, back to the rest position, and it's going to take half of a second to do that. All right, so that's what the amplitude and the period. The amplitude tells us how far we're moving, and the period tells us how long it takes to do one full cycle. Right, so it's going to take half a second to do that. Right, the frequency now, to do the frequency, like there was a formula that I had up here before for frequency, but really remember, frequency is just the reciprocal of the period. So if I know the period is 1/2, the reciprocal of 1/2, if I flip that fraction over, is 2/1. So the frequency is going to be 2 cycles per second. Right, which makes sense. If it takes half a second to do one cycle, well, there's 2 halves there's 2 half seconds in 1 second, and so you're going to do 2 full cycles per second. All right, that's the reciprocal relationship there. All right, so rest position, 10 inches down, 10 inches up, back to the rest position. That takes half a second. You can do that twice in 1 full second. All right, so our frequency is 2 cycles per second. All right, so that's our amplitude, period, and frequency, just using the definitions we had up here before. To pull those numbers out of our equation and identify what they mean. And now if I want to sketch the graph of this, all right, well, my amplitude is 10, so I'm going to have a maximum of positive 10 and a minimum of negative 10. My period is going to be 1/2. Right, so let me actually do 1 full second here. Here's my 1/2. Right, so my graph is going to do a full period between 0 and 1/2. All right, so between 0 and 1/2, I'm going to split that up into 4 sections, or four pieces. All right, so I cut between 0 and 1/2, I cut that in half, and then each of those halves I cut in half, and now I'm dealing with a sine function. And remember, the graph of a sine function starts at the origin. It starts out at that rest position, and then it's going to go up from there. So it's going to go from 0 up to 10, back to 0, down to negative 10, and then back to 0, and that's going to be 1 full period between 0 and 1/2. Right? That's why I take 0 to 1/2, 1 full period, and I split that into 4 pieces, and then I just mark my points, middle, top, middle, bottom, middle. And if I do that correctly, then by the time I get back to the middle and I finish the whole cycle, I'm at the end of that first period. And then to do a second period of this, I just do the same thing. So between 1/2 and 1, I cut that into 4 pieces, or cut it in half, cut each of those in half, and then I do the same thing. It's going to go from the middle to the top, to the middle, to the bottom, back to the middle, and then there's my graph of y equals 10 sine of 4 pi t. Right? That's our model for this simple harmonic motion. Right? And since we're starting at the rest position, that's why we're using the sine function. Right? If this spring, say this hand here is the rest position, we're starting there, and then we're going 10 inches up, back. Right? If we had started at our maximum point or at our minimum point here and then let the spring go, we would have used the cosine function to do that instead of the sine function. Right? So whether you use sine or cosine, once again, is all about your starting point. If you start from the rest position, it's the sine function, because the sine function starts at that middle level. If you're starting from the highest amplitude, that's when you use the cosine function, because the cosine function starts from that maximum point. All right, so that's an example of simple harmonic motion. I'm going to do a couple more videos about phases and phase shifts and things like that. So make sure you check out those. There's other stuff involved with harmonic motion that we'll get into in some other videos.